No choice. Is that what you said that? All right. I want to begin with consolidated some of these clicker questions. And since I didn't get to any, let's start there. Pull your clickers out. And we'll use these to start us out with some review. Give you points in the process. All right. So I went back through the 4 chapters and picked out some I thought would help us review. Enough said. Polling's open, channel 44. Go ahead, guess away. And you know what? If you're not sure, discuss it with your neighbor and answer. That's fine with me. Some people are still showing up. Some people are still pulling out their clicker. So I'll give you a few extra seconds on this first one. I can see the majority's voted, but not everybody. She's got her clicker out. There we go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And, ooh, it's more split than I thought. Most of you thought it was A, translational motion, over half of you. But 40% of you thought it was C, internal vibrational motion. Okay. The correct answer is, translational motion. The motion of molecules that most affects temperature. Remember, temperature by definition is the average translational kinetic energy of the molecules. They can be moving other ways, and that's why I chose this one to reemphasize that. There's other forms of energy included in internal energy. Temperature is one of those, this translational motion, moving like how we're used to moving, you know, when I walk from here to here, or over here, or around. They kind of wiggle. But they can also rotate, they can spin, they can vibrate. Molecules can vibrate. That's not part of temperature. That's not what temperature measures. It's the translational kinetic energy. Yeah? Yes, absolutely. A molecule can do all 4 at the same time. Temperature is only a measure of that one type, though. That's what I wanted to reemphasize. So all of those are part of internal energy, but temperature is just one aspect of that. Remember, we can have our 2-liter bucket of water and our 1-liter bucket of water. They can have the same temperature, meaning they have the same translational kinetic energy, but the bigger one has more internal energy because there's more of them. We can also have something smaller, less of something that's hotter, has a higher temperature, but we can still have more internal energy in something that's cooler if we have more of it, or if it's got all these other different forms. Other questions about that? All right, next. Polling is open. Let's see if you got this absolute zero and Kelvin scale thing learned, or at least one main point where absolute zero is. So that's what scientists like to use more than Celsius. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 73% C. So 3/4 of you think it's both. You guys are correct. The rest of you need to learn that. They're the same point, they're just different scales. Absolute zero is 0 on the Kelvin scale, negative 273 on Celsius. And that's how you can convert between the two. So if you're on the Kelvin scale and you want to get up to 0 degrees Celsius, you come up 273. Because in other words, 0 degrees Celsius is 273 Kelvin. Absolute zero, too, I want to emphasize with that is, I don't remember if I did it or not. It's less important unless you're like, oh, this is going to be on the test. But I wanted you to know, at absolute zero, do the molecules, let me rephrase, as they approach absolute zero temperature-wise, what happens to the molecule's motion? It slows down, yeah. And all those forms are going to slow down as it gets colder, but its temperature does too. If it could get to absolute zero, what do you think happens? Yeah, and that's actually, a lot of you said stop or no motion. And it's not actually true. Its temperature would be 0, which means its average translational kinetic energy would be 0. Average. Some of them still might be moving. They still might have some other forms of motion. But what's critical here, if it can reach absolute zero, there's no energy in it that's available to be useful. Because now we've discussed heat engines and thermodynamics. If it has any energy left in any form, it's not useful to us. There's no way we can harness that at absolute zero. Somebody had a hand maybe? Guess I answered it. All right. Next. Go. What's heat? What's heat? I want to see if I failed here. The whole first chapter was heat and temperature. We've been using those for the last 4 chapters. Oh, you guys are cruising. Most of you are in. So 10, 9, 8, 7, 6. You can try to get it in if you want, if your clicker's handy. She's got hers out. Is it working? That's all right. I haven't seen it yet. Did it take? You on channel 44? Oh, okay. Well, you get the next one. 75% C. Good job. For those of you that answered A, you really need to go read the chapter better. That's all I have to say about that. Yeah, heat only flows. It's a transfer of energy. It kind of incorporates that whole internal energy. Temperature is just a measure of the translational kinetic, but heat kind of incorporates all that, and it allows it to flow only when there's a temperature change. Very good. Questions about that one? Okay, go. Now you know the little difference. When you add heat to something, what can happen? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, and... Okay, 58% of you said it may or may not rise. However, 38% of you said it will rise. Somebody that said B, give me an example where it wouldn't rise. Yes? Water to steam. If water is being converted to steam, does the temperature change? What's the only way water can get to steam? By adding what? Heat, transferring heat to it. And it increases its internal energy, but not its temperature. So yes, the correct answer is B. So when you add heat to a system, remember from the first law of thermodynamics, that can go into increasing the internal energy. But remember that could be, melting, changing bonds, causing vibration, not necessarily making it hotter. When water boils is another example. It gets to 100 degrees Celsius and it stays there until it converts to steam. So just because you add heat doesn't necessarily mean the temperature rises. Those that put A, questions? All right, go. Lest you're confused, I'll recap. Got aluminum and copper. Aluminum has more specific heat capacity than copper. So if you add heat to both of them, equal amounts, who's going to heat up faster? I'll even remind you, specific heat capacities, thermal inertia, a resistance to change. Most of you are in, so 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 83% B. Copper. Good, good. Copper has less specific heat capacity, less thermal inertia, less resistance to change. So for the same amount heat coming in, it's going to affect its temperature at a higher rate. It will increase its temperature more quickly. Yes? Yes. And that's whether you're adding heat or removing heat. It would cool more quickly as well. Let's say you got the aluminum and the copper to the same temperature. We know it would take longer to get the aluminum to that temperature, right? Now let's say they're there now, equal masses, and you just let them cool. Who will cool off more quickly? The copper. Yes? There's a connection, but not completely. So yeah, you can't have, there are cases where some things have a higher specific heat capacity but don't expand as much as something else. It has to do with the binding energy as well. The crystal lattice, if you will, of the solid or something. So that can change. Okay. Go. You can tell the temperature of a star. Is this enough to do so? And what can you tell me? While you're answering, what form of heat transfer does this involve? Radiation, good. Electromagnetic wave is emitted. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ooh, we're split. In the 40s, B and C. So you guys are debating between blue and white. All right, convince your neighbor. It's between blue and white now. I'll give you that much. Polling's open again if you want to revote. I will tell you it's B or C. 10, 9, 8, 7, 6, swallow, 4, 3, 2, you guys aren't voting now. Okay. And, oh, you're getting it? Okay. Oh, now we got an answer I. That's good. That must have been a mess up. 62% of you think B. More of you. That's the correct answer. Blue light has a higher frequency, more energy, shorter wavelengths. Red has lower energy, longer wavelengths, lower frequency. White is all the colors, visible colors. So there's a spread. You got red, orange, yellow, green, blue. Blue star would just have blue, whereas white would have some of the less energetic as well. So a blue star is hotter than a white star. And honestly, I didn't know if all of you would know that when I asked this, but hey, we've learned. That was cool. So when you're, checking out the stars, you can think of that. Or a fire. A blue flame in a fire should be hotter than a white flame. Okay, how about this one? Absorbers and emitters. Let's put that cold pizza in a hot oven. What happens? What's that mean? While we're answering, how does a pizza heat up? What forms of heat transfer in a conventional oven? Conduction, how? Yeah, from the trays. Yeah, it's in contact with that to the stone. Yeah, direct transfer. How else? Convection. Heats up the air next to the oven, and it circulates, and that gets over to the pizza. How else? Yeah, you see your elements glowing red? They're getting hotter, the red, so they're sending out electromagnetic waves, and they can travel through empty space to the pizza and heat it up. All right. Yeah. I'm saying let's put it in and try to cook it. We put it in, shut it, turn it on. Yeah. All righty. I'm closing. 52% of you think it's A, but some of you think C. It's a net absorber. Do you expect your pizza to get hot or cold? Hot. You're cooking it. And so its temperature is increasing. So it must be absorbing more radiation than it's emitting. So it's a net absorber. True, it's doing both. And as it heats up, it's going to radiate even more. So it's absorbing and emitting all the time. But if it absorbs more than it emits, then it's a net absorbing. It's getting hot. It's going to raise its temperature. That's why we put it in the oven. If you set it out on the table, it will be a net emitter. Yeah. Its surroundings, the pizza around its the air and the oven. Does it have more internal energy or less internal energy than the cool pizza? Put the cool pizza in the oven. Does the surroundings in the oven, the surroundings, have more internal energy or less internal energy? As a whole. You put the cold pizza, the same question, but I was not curious. The internal energy of the surroundings, the immediate surroundings of the pizza, so the air inside the oven itself, does those surroundings have a greater internal energy or less? I would probably say so in practical real life, but I bring this up because heat flows when? Temperature difference. So we know it's hotter than the pizza because heat's flowing from the surroundings to the pizza. Technically, I don't know if the internal energy is larger or not. In reality, it probably is because of an oven gets really hot and whatnot, but we'd have to go take some measurements. Remember the thing with the hot cup of tea and the cool big vat of water? the vat of water probably has more internal energy, but heat flows from the cup of tea to the water. I'm just trying to emphasize that part again. Heat doesn't flow because of a difference in internal energy. It flows because of difference in temperature. Don't get confused. All right. Some of this later stuff. Pulling open. Going to transfer this heat now. What does that? What's it called? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 8. 83% D. All of the above. Very good, very good. It doesn't matter which way it's going, which way you're trying to pump. If a heat engine is all those, a refrigerator and an air conditioner are examples of that. We're trying to transfer. We're using heat to do some work. We put work in to try to move heat. That's a heat pump, heat engine. They're interchangeable terms. Yeah, I can go either direction. Very good. All right, how about these phase changes? This came up a lot, so I'll ask this one. Steam condenses the water. What's that tell us about the energy? You guys picked a good day to show up, asking all these questions. Ooh, you guys are a little slower on this one, huh? Steam to water, gas to liquid, condensation. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 67%, 2/3 of you, B, releases energy. That is correct. Gas has more energy. When it goes to liquid, the liquid has less energy. In order to condense, the steam must give up some energy. If that doesn't mesh with you, think of it the microscopic way. The gas molecules are going to have more energy. They're moving around faster. The ones that slow down by running into something, or they're just on average a little slower than them individually are slower than the average, then they could combine and coalesce, condense. They were the less energetic ones. They leave the more energetic ones behind. They left. So energy is released from the steam. Whichever way it works. I personally like, if you're going down from gas to liquid or liquid to solid, the object must release energy. And to go up, change phase the other direction, it's got to absorb energy. Make sense? Okay, we discussed this one. Steam burns hurt more. Why? This is the idea you could touch 100 degrees Celsius water or 100 degrees Celsius steam. Steam can get hotter than 100 degrees Celsius. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 70% B. Very good. Steam can get hotter than 100 degrees Celsius, and thus it would have even more internal energy. But if they're at the same temperature, 100 degrees, steam has more internal energy because Remember that 540 calories per gram of water? 1 gram of water absorbs 540 calories and becomes steam. It now has that much more energy than the water at the same temperature. So it's because of that phase change that steam has a lot more energy. And so when you put your hand in it, what's the steam going to do on your hand? Condense. Good. The steam is going to do what to energy? Last question. The steam does what when it condenses? Releases energy. Where does that energy go? So you absorb it and you gain that energy and you heat up. Correct.
When the phase change takes place, it becomes steam. Can steam have different ranges of temperature, or is it just one temperature, just like boiling water?
So you got water. It starts boiling. When it gets to the boiling point, and ideally at room sea level and everything, 100 degrees Celsius, and it stays at that temperature. What does it start to do? Change phase. The energy is now going into not changing the temperature, but changing phase, and some of it starts becoming steam. Meanwhile, the rest of the water is still changing phase at 100 degrees Celsius, but that steam takes some energy away from the water. And if you can trap that, put a lid on it, the steam can increase temperature as well. After it changes phase from liquid to gas, it can now increase its temperature. So it'll be, water. 90, 91, 92, 95, 99, 100. Then it converts to steam at 100. You keep putting heat in, and the steam's there to absorb it. The steam can now go to 101, 102, 105, 500, and so on. So you're always putting heat into the water, but the water's constantly boiling, converting to steam. That takes energy away, that cooling effect. But you're still putting heat in, so the temperature always stays the same while you're boiling. Say that again?
Doesn't D imply B?
D imply B, gaseous. Yeah, technically, but it's not the best answer because B is Y, D implies it. The fact that something is in a gaseous state means it has more internal energy than its corresponding liquid energy, yes. B makes that more explicit, so yeah. But that's why it's a clicker question, not an exam. There was one over here too? Go ahead.
So heat, to say something is hot, not
You can say something's hot, but that tells me its temperature is greater than something else. No, don't think of something as containing heat. Yeah, heat, because heat's the transfer of flow, just like something doesn't contain work. That one makes more sense to me, so I always try to keep those together. It's just awkward to say Ryan contains work, possesses work. He can do work. I can work on him. So same with heat. And whether that heat moves is based on how hot it is compared to its surroundings. Hot being the temperature. Oh, yeah, I think this is good. Let's see. Okay, you should get this one. Ice changes phase to become water. In order for this ice to melt and become water, it's got to ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Yeah, look, okay. About 80% A absorbed. Good. Yeah, it's got to absorb water energy to do that. It's a phase change. The direction it's going. It'll give off if it's going the other way. Okay, we had a homework question on this one. And I asked this to, because I'm not sure how you all did on it yet. I hope you get it, Ryan. I like this one because it kind of makes another connection between what you just asked about. You say something's hot, that's its temperature. But then you got this internal energy. So if we double the internal energy, what's that tell us about the temperature? That's what this one does. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, kind of across the board, but definite majority, 42% say A. Glad I'm asking it. This is one to emphasize that the temperature, when you're dealing with thermodynamics, needs to be the absolute temperature. So doubling the internal energy, making it twice as hot, you can't use Celsius. So talk to your neighbor and revote. So the answer is not A. I know. So just doubling, if it's 5 degrees Celsius, doubling it, you can't just go 10. Oh, it's 10 now because it's twice as hot. Convert that to Kelvin, the absolute scale. Then double it and convert it back, since I didn't give you any options in Kelvin. So when you're thinking of internal energy, you have to think the absolute scale, which is Kelvin. So convert that to Kelvin, then double it, convert back. Yes, Ennis? Would I have it at?
Like when you ask the question, you say, what is the temperature in Kelvin, as opposed to what is the Celsius, because that's specific.
Oh, would I ask? Well, that was my point here. The only answers are in Celsius, so you have to think in terms of Celsius, but you can't solve it in Celsius. And I don't intend to ask this, if you will, tricky, hard of a question on the test. But this is to emphasize something I feel like we didn't cover as well, this doubling of internal energy. When you do that, think in terms of Kelvin.
So when you use the term temperature, we should always think Kelvin.
You're safer. Yeah. There's sometimes you can get away with Celsius, but only because the incremental changes. Remember ideal efficiency? That has to be Kelvin. I'll get you started if you haven't. What's 5 degrees Celsius in Kelvin? 278. You add 273 degrees. So 5 degrees Celsius is 278 degrees Kelvin. Now we can double. Twice that is? I don't remember what. And then we 278. We double that and it's. Now we convert that back to Celsius by doing what? Subtracting 273 back off. And as I was explaining to Ennis here, I don't intend to make one this complicated on the test. It's to emphasize this point that with thermodynamics, remember ideal efficiency? You got to think in terms of Kelvin.
Can you explain again why we have to convert it to Celsius or to Kelvin?
Kelvin's, we have to convert because Kelvin is an absolute scale. In our world, we're used to Fahrenheit. The rest of the world's used to Celsius. They're not based. They're based arbitrarily off by convention with like body temperature, and when water freezes and whatnot. They're not an absolute. They're relative to something else. The Kelvin scale is absolute. It has a 0 point, and nothing beyond that. So in thermodynamics, and scientists like the Kelvin scale. So when you're thinking in terms of internal energy, well, that's relative to what? You got to have some 0 point, and the only scale that has that is the Kelvin. That's why you can't just double the Celsius temperature. Because remember, temperature is only a measure of the average translational kinetic energy. We double that, well, that tells us twice that speed, but it doesn't tell us anything about the internal energy. That's why we're converting to Kelvin. Him first.
I'm just like, on the homework I had 0 degrees Celsius, and
I know.
that was kind of obvious why that would work. Still heat, but if you double 0, it's just 0 again. So you have, that's what tipped me off right away. Oh wait, we gotta use
Yeah, that's why I'm asking, another reason I'm asking this, on the homework we had one where it started at 0 degrees Celsius. And if you double zero, I'm sure most of you thought, oh, double zero, you can't. Well, it must be 0. And you put that in and realize it's the wrong answer. Something else must be up. So only one student ever asked me about it. But it's the same thing. You convert it to Kelvin first, then double it. Convert back. Yes? Do you still have a question?
I'm going to have to study again later because I'm lost. Never mind, let's move on. I can handle the 0 point on the test.
Well, and again, I'm not asking in this form. I mainly want you to realize if you're doubling the internal energy, you got to think in terms of Kelvin. It's the only temperature scale that's absolute. Celsius and Fahrenheit are relative to something else. You can't, it's like your potential energy. I raise this up and say it has potential energy. Relative to what? Because I can say this has so much potential energy relative to the table, but it has a different amount of potential energy relative to the floor. It's like you need that 0 point, a baseline. The Kelvin scale allows you to do that. So anyway, the answer with this one is, well, y'all got D that time, yes. Yes.
There's another way to do this if I'm not sure if we'd ever do another doubling question, but if you just remember 0 degrees Celsius doubled is 273, then you just double whatever the Celsius temperature is added onto it. Will give you your answer. So for this one, it's 5 degrees Celsius. 0 doubled is 273 degrees Celsius. Is that one?
I see your point, and for lack of duration, I'm not going to repeat that for the camera, but yes, mathematically it's the same thing. It's just more, for some people that's useful, and others it's more steps. So, yeah. Yes.
Why is it that you add it the first time and you subtract it?
We have to convert it to Kelvin in the first place. Remember, 0 degrees Celsius is 273 Kelvin. So 5 degrees Celsius is 278. Now we have an absolute value. We have something that we can actually double and know it means something. Yeah, Ennis?
Absolute value is -273.
Yes. Absolute 0 is -273 Celsius.
But then if you were to go to 5 degrees Celsius, you just add 5 degrees Celsius on top of the 273, you get 278.
Correct. Add them.
It's double, which would be 278 Celsius.
You okay with that? Did I do that right? That's where the doubling of the internal energy occurs. So it's 556 Kelvin now if we make double the internal energy. So that's the temperature. I didn't give you any answers in Kelvin, so we have to convert that back to Celsius. For the homework problem is exactly the same. That was just 0. So we get 273 in the first place. 0 plus 273. And then double 273. Get that, Yes?
I was realizing when I'm about to ask it.
Okay. That should be worked out too in the key to the solutions that you can now see since Saturday. Yeah. Okay, your turn. What other questions do you have? Let's see.
Okay, do you remember when we talked about, sorry, okay, so how your desk is at room temperature, but the middle part of it feels colder?
Yes. So yeah, the wood on your desk and the metal on your desk are at the same temperature, correct? So they've had time to come to equilibrium with the temperature in the room. That just tells us, again, the measure of their average speed is the same. But when you touch metal and you touch the wood, heat transfers now because you're not the same temperature as they are. You're warmer than the room. And heat flows from the hotter object, you, to the colder object. Which one will raise its temperature quicker? The metal, because in that case it has a lower specific heat capacity, and so that's going to draw more heat out of you more quickly. And so if to that hand, yeah, touching the metal, it'll feel colder because it's the energy's going out of it faster than the wood. Another way to think of that is the wood's a better insulator for heat transfer. It's still transferring out, just more slowly. So the same with carpet on a floor. Tile floor versus a rug. Other questions that are bothering you guys?
Last class where you talked about the second law of thermodynamics, you said that without a device or something, that heat won't flow from cold to hot. And I was thinking about that, and I think I might be thinking of it wrong, where that device actually just, it's kind of like an air conditioner where it takes air that wouldn't naturally flow from one place to another and it forces it to do that. It doesn't actually change the way that heat is transferred. That makes sense.
I'll repeat and tell me if I'm getting it. Yeah, it doesn't change the way heat's transferred. We still have the same methods. Heat naturally flows from something hotter to something colder. It'll do that on its own if it can, has a way to get to it. It won't go from cold to hot on its own. It can, though, if we force it to. And to do that, we got to put work in. A heat engine, heat pump, a refrigerator, an air conditioner. Because it doesn't want to just do it naturally. So you're right. Heat will not flow from something colder to hotter unless we force it to move by doing work. We got to exert energy to do that. And in doing so, we're going to increase the overall entropy because we had to do work to do it. Who has more entropy? What do you think? Steam or ice? Yeah, there's more disorder in steam. All those molecules, picture them moving around in a random way where they're nice and structured and ordered in ice. Entropy is the measure of disorder. So the more order you have. So see, you can take steam and convert it to ice, can't you? But it takes work. You got to put energy in to make it go that way. It releases energy to remember, steam condensing. That increases the entropy there. Question 9 on the homework. Grab the right one. To increase the temperature of 50 grams of water by 2 Celsius degrees. So we have 50 grams of water, and we want to change its temperature by 2 Celsius degrees. Is it going to have a phase change? Do you think this is going to convert to steam?
I guess it depends on how hot the water is at the beginning.
It sure does. Dang. I'm going to fix that question and make it even better. I can look at your homeworks. That one, you can plug it right into this equation from your book, 50 grams specific heat of water, change in temperature, and you get 100 calories. Or realize from the text that every gram of water rises 1 temperature, or 1 Celsius degree for 1 calorie. But basically that's doing the same math. You get 2 times 50. It ends up being 100. Every gram takes 1 calorie to go 1 Celsius degree. Well, we got 50 grams, and we're going 2 Celsius degrees. Now here's one where if you did this in Kelvin, you'd do it right as well, because the change in temperature is the same on the Celsius scale as it is on the Kelvin scale. A 2-degree change of Celsius is 2 degrees of Kelvin. Does that help, Ennis? Few heat engines as you think of other questions, just because they were kind of fun and I brought them out last time. This is called a Peltier device. It has 2 fins that I put in 2 different temperatures. This one's room temperature, and this one you saw me just pour liquid nitrogen in. In between here, sandwiched is the Peltier device. It's like 2 ceramic materials sandwiching a bunch of bismuth. And it, we're not getting into, converts a temperature change. As it flows from one side to another through the bismuth, it allows electricity to flow, and it's connected to the motor. This one can do a similar thing. And heat engines, these are just to emphasize that in order for them to work, you got to do something. And these are both driven by temperature differences. Heat flows from hot to cold. This one, there's a piece of styrofoam in there and it moves up and down. This is full of liquid nitrogen. It cools the bottom. Those molecules are moving less energetically. Up top is the hot side. And the heat wants to flow from the hot to the cool. So it expands and pushes the piston, the piece of styrofoam. Some of it leaks around. It expands and it cycles through. And they got some cam levers here, to make it work. But it all works because this side's hotter than this side. Heat flows, and when it does so, it can do work. So we're putting heat into this, causing heat to flow, and you get an engine. Same with this guy. And all of you probably drive cars, so I figured I have to at least show this. Okay, I guess it was on. There we go. Spark plug. Can you see the little flash? They just use little valves and the piston. So let's start with the spark. Right there. Boom. The spark ignites the gas. The gas heats up. It expands. And when it expands, it does work. That's the power stroke, and it drives it down. Well, then momentum, going in a circle, brings it back up, and it pushes out the exhaust gas. They use timing to open up a valve and the exhaust gases go out. That is the second law of thermodynamics. We can't reuse that gas. Its entropy is increased. It contains no more energy. We can't reburn it. So some of the heat from the hot side has to go down here. This, the way I've drawn it, violates the second law of thermodynamics. We're getting work out of this without any exhaust. That can't happen. So that's why we have an exhaust. There, exhaust. Then as it pulls back down, this valve opens. As it expands, it lowers the pressure and pulls new fuel in, compresses it, and sparks and starts over. But that's the basic 4-stroke combustion engine that most of our cars still work on. It's a heat engine, and they're obeying the laws of thermodynamics. This one does obey the first law of thermodynamics because you see the amount of energy that came out is done at work. But this does not abide or obey the second law. This one obeys the second. See, it comes down and comes out, but you're getting the same amount. You'd have to be less. You can't get all of that heat to work. So again, just to emphasize conservation of energy and not. Other questions you guys have? If you think of some before Wednesday, you can call me or email me. Okay.